Hello everybody and welcome to this exam question walkthrough where we're going to take a look at some multiple choice questions from Isomerism and Nomenclature. You can download these organic chemistry questions from the description, then watch my video back and see how you got on. In this question we're being asked which compound has a molecular formula that is different from the others. If we work our way through these, we're presented with skeletal formulae, and what you have to remember is we never show hydrogen in skeletal formulae. So for instance here, we've got a carbon atom with 3 hydrogen atoms attached to it. Here we've got another carbon atom, but the carbon has already got 4 bonds, so no hydrogen there. And there's another one here in the exact same position, so no hydrogen on this one because it's already got its 4 bonds. And then this one has another 3 hydrogen attached. So altogether, that makes C4H6O2. And then in the second one, if we go hunting for the 4 carbon atoms, there's one here and here and here and here. So this is C4. There will be 2 hydrogen attached here, 1 here, 1 here, and 2 here. So that makes H6, but there's another H on both of the OH groups. So this is C4H8O2. So we've immediately hit on 2 different molecular formulae, so all we need to do is find one more that matches one of these first 2. So here we've got a ring of 4, so that's 1, 2, 3, 4 carbon atoms, so it's C4. There'll be 2 hydrogen atoms in this position, 2 in this position, only 1 on both of these 2 sides, so that's C4H6 so far. Then there's the 7th and the 8th hydrogen, so this will be C4H8O2, which matches what we got for B, which means that A is the one that's got a different molecular formula to all of the others. And we can explore D just to complete the set. We've got 1, 2, 3, 4 carbon atoms, 3 hydrogen atoms here, 1 here, 2 here, and 1 at the end, and then this one at the top makes 8, and so this is also matching B and C. Here we're being asked what the number of structural isomers of C4H9Br is. Now, structural isomers can be functional group or chain or position. There is no way we can get a different functional group from this collection of elements, so we are looking at chain and position. So the most logical sequence that we could get for this is a chain of 4 carbon atoms that looks like this. And then the bromine could either be in position number 1, like this, or we could have that same chain of 4, but the bromine could be in position number 2. So that is 2 structural isomers so far. But then if we had a different chain length, so a chain length of 3 instead of 4, we would have a branch in the middle. Then we've got the situation where we could have a bromine also in the middle, or we could have a bromine on the end. And that's our only 4 permutations that we've got. So there are therefore 4 structural isomers of C4H9Br. Which compound is not an isomer of the following compound? So we've been shown a skeletal formula of something that looks like it's cyclic, which means it's got a carbon atom here. Now, carbon atoms have got 4 covalent bonds each, and we're only being shown 2. That means there are 2 unshown hydrogen atoms for this carbon atom. And then there's another carbon here with another 2 hydrogen atoms we need to add, same again here and same again here, and this is the oxygen. So this is C4H8O. Now all we need to do is look at our 4 options and find the one that is not an isomer of this compound. So in other words, has got a different molecular formula. When we count along, we've got 1, 2, 3, 4 carbon atoms, and we've got 8 hydrogen and 1 oxygen. This is not the answer. Same again for B, that is also C4H8O. C looks a little bit trickier. We've got CH3 twice, so that means that's C2, 3, 4, and then hydrogen 6, 7, 8. This is also C4H8O, which means D must be the correct answer for not being an isomer of our compound that we've been shown. And in fact, we've got 1, 2, 3, 4 carbon atoms, so that's still correct, but 2, 3, 4, 5, 6 hydrogen. So this is C4H6O, and the correct answer because it is not an isomer of this. Here we're being shown a very complicated looking flow chart which shows one molecule being converted through a number of steps into different compounds, ultimately ending up with something that is called polymethyl 2-methylpropenoate, which is commonly called Perspex. However, our question that we're being asked is, which of the following is not a structural isomer of compound M? So all we need to do is look at compound M in more detail and compare its molecular formula to the molecular formulae of these four options. When we do that, we can see that the molecular formula of M is C1, 2, 3, 4, H2, 5 and 6, and O2. So C4H6O2. When we look at A, it's just a case of counting up the carbon atoms, C4H6O2 again. So A is the wrong answer because it is a structural isomer of compound M. B, similarly, we've got 4 carbon atoms again, we've got 6 hydrogens, 2 oxygens, so that is also an isomer. C has actually only got 3 carbon atoms, so it does have 6 hydrogen, but this is going to be C3H6O2, so it is not a structural isomer of M because it's got a different molecular formula. So C is the correct answer to this question. This question is asking us what the number of structural isomers is for C3H2Cl6. There's 3 types of structural isomer. There's functional group. That can't be the case here because we've got a halogenoalkane and there is no functional group isomer of that. There's also chain isomerism. We cannot have a different chain length when we've only got 3 carbon atoms. So that leaves us with position isomers to explore. We have to have a chain of 3 here and we're exploring where our 6 chlorine atoms could go. But in fact, our job is made easier if we just simply think about where those 2 hydrogen atoms could go and let the chlorines just be the rest of this molecule. And so we could have 2 hydrogen atoms on the left-hand carbon of the chain, or the right-hand. That would be the same isomer, they are on an end. Or we could have both of those hydrogen atoms on the middle carbon, and so that's another possibility. And then that's the end of having 2 on the same carbon, so we're looking at where can we put 1s. Well, we could put 1 hydrogen atom on each end of our chain. Or we could have 1 on an end and 1 in the middle. And that's the end of our different combinations that we can have. So the correct answer is C, there are 4 structural isomers. Here we're being asked how many isomers there are of C3H9N. Now, this is going to be talking about structural isomers, and there are 3 types of structural isomer: functional group, chain, and position. There isn't really any other functional group that we can have here other than amines because of the number of hydrogen atoms that there are. Then we need to keep in mind position and chain. The simplest amine has got an NH2 group sticking out of a carbon chain. So let's begin with this. So this would be propyl amine. And then instead of having the amine group on the end, we could have the amine group in position number 2. And this is the end of our chain of 3. Then we can explore having more than 1 different carbon chain sticking out of our nitrogen. That's called an alkyl group. So here I'm showing 3 separate methyl groups sticking out. So this is a 3rd isomer that we could have. Now, instead of having all 3 of those being methyl groups, we could also have a chain of 2 sticking out of our nitrogen and a chain of 1 the other side. And this is ethyl-methylamine, and this is our 4th isomer and our last isomer. So the answer is C. There are 4 isomers of this formula. Which one of the following is a pair of functional group isomers? So functional group isomers have got the same number of atoms of each element, but they are arranged differently in such a way as to give us a completely different functional group. So what we need to do is look at each one of these in turn and determine what the functional group is. So for the first one, we can see we've got this COOC group, and that makes this an ester. On the right-hand isomer, we also have an ester. So these are the same functional group, and therefore these aren't functional group isomers. For B, if we have a look at this structure, we can see actually that this is a hydrocarbon and all of the carbon atoms have got 4 bonds to 4 different elements. So this is actually just an alkane. And then when we look at the one on the right, this is also an alkane. And so these aren't functional group isomers. When we take a look at C, you should hopefully quickly recognise this alcohol functional group. And then we've got an oxygen sandwiched in the middle of a carbon chain. This is very definitely a different functional group. Now, a lot of exam boards don't require you to be able to name this functional group. This is called an ether, and this one will be called methoxyethane. But what's important for this question is it's definitely not an alcohol. And so these are functional group isomers because they've got the same molecular formula, but a different structural formula and a different functional group. If we take a quick look at D, we can see that we've got an alkene functional group, and we've also got the halogen chlorine attached as well, so those will be the same functional groups. How many structural isomers are there with an unbranched carbon chain that have a molecular formula C4H8Br2? Structural isomers can be chain, position, or functional group. Now, there is no functional group isomer of halogenoalkanes. We have to use unbranched carbon chains, so that means there's no chain isomerism, so we're only working with position isomers here, which means we're going to be moving those 2 bromine atoms around to see how many combinations we've got. We could have both of those bromine atoms on the first carbon in the chain, or one on the first carbon, one on the second, or one on the first and one on the third, one on the first carbon and one on the fourth. That is 4 possible isomers. Then if we put a bromine atom on the second carbon atom in the chain and another one on the same carbon atom, that's a 5th isomer. And then last of all, we could have 1 bromine atom on the second carbon in the chain and 1 on the third. So that gives us a total of 6 possible isomers of this formula. Here we're being shown the structural formula of cyclohexene, and we're being asked what the general formula is for cyclic alkenes, such as this one. Now, general formula is like the nth term, where you would say CnH2n plus 2 for an alkane. This is because every carbon will typically have 2 hydrogen attached to it, and there's the 2 on the ends as well. When you get a cyclic alkane, you don't have the 2 end carbons in the chain, and it is just CnH2n. Alkenes also have the general formula CnH2n, and that makes them functional group isomers of cyclic alkanes. The reason that they are CnH2n is because the carbon atoms have got a double bond between them, which means that there is 2 fewer hydrogen atoms in the structure. So when you've got a cyclic alkene, there will again be 2 fewer hydrogen atoms than there is for a typical cyclic alkane. And so instead of it being CnH2n, it needs to be CnH2n minus 2. And you can prove that by looking at this specific example. We've got 6 carbon atoms in a ring, and if we consider each carbon atom in turn, we can see that this carbon atom at the bottom has only got 2 covalent bonds, which means there'll be 2 hydrogen there, 2 here, 2 here, 2 here, and then the 2 that are in the double bond, well, that will only have 1 hydrogen atom, this will have 1, and so overall this is going to be C6H10. So we double the number of carbon atoms and then we take away 2 to get the number of hydrogen atoms. And so the general formula is going to be B. How many structural isomers have the molecular formula C4H9Br? Well, structural isomers come in 3 different forms. You can have functional group isomers, chain isomers, and position isomers. There are no functional group isomers for halogenoalkanes, so we're just looking at the second and the third. In terms of chain isomers, you can have a straight chain of 4 carbon atoms, or you can branch that chain, have a chain of 3, and a methyl group sticking off the middle carbon. If we consider the straight chain carbon skeleton, we could have a bromine atom on the end for 1 bromobutane, or on the second position for 2 bromobutane. For the branched halogenoalkane, we could have a bromine atom in the middle on the same carbon as the methyl group, or we could have the bromine on an end, on a different carbon to the methyl group. So the correct number of structural isomers is 4. How many isomers have the molecular formula C5H12? In terms of structural isomers, there is functional group and chain and position. This is the general formula for an alkane, and there are no functional group isomers for alkanes. This is a saturated molecule with only carbon and hydrogen, so there will be no position isomers either, so we're just looking at chain. We start with a chain of 5, so this is pentane. And then we need to consider branched alkanes. So this is butane. We could have a methyl group here, so that would be 2-methylbutane, or we could have a methyl group here. That would also be 2-methylbutane. So in fact, it doesn't matter where we put our methyl group, and we don't even need that 2. This is methylbutane. Then we could have a chain of 3, so we've got a propane starting point. In order to get 5 carbons, both of the methyl groups have to be on position number 2, so this would be dimethylpropane. No numbers required in this instance because there is no other position that those 2 methyl groups could go on with this still being propane at the end of it. And so we've run out of potential isomers now. I've drawn 3. That means the correct answer is B. There are 3 isomers of C5H12. This question is asking us how many structural isomers there are with the molecular formula C3H6BrCl. There are 3 types of structural isomer: functional group, chain, and position. There are no functional group isomers of halogenoalkanes. When you've only got 3 carbon atoms, there are no chain isomers that are possible, so we're just looking at position. When approaching this question, the best thing to do is draw a couple of the carbon skeletons. We've got 3 to draw. We've got to put a bromine atom and a chlorine atom onto each of these skeletons, and they've got to be different each time. First of all, the bromine and the chlorine could both be on the same carbon atom. That could be the end carbon atom, or it could be the middle carbon atom. That's 2 isomers. Then they could be on different carbon atoms. The bromine could be on the end, and the chlorine in the middle, the bromine on one end, and the chlorine on the other end. Or the chlorine could be on the end, and the bromine atom in the middle. That's the last of the possibilities. If you're not sure whether there are more possibilities, it's a good idea to name the things that you've already drawn and then see if any other naming combinations are possible. There aren't any more possible isomers here, so the correct answer is B. There are 5 isomers. This question is asking us for the total number of structural isomers with the molecular formula C2HBrClF3. There are 3 types of structural isomer: functional group, chain, and position. These are halogenoalkanes that we're going to be drawing, and there are no functional group isomers of them. There are no possible chain isomers either, not with only 2 carbon atoms to arrange, and so we're just looking at position. My suggestion for how to approach this is actually to ignore the fluorine atoms. And what I mean by that is consider where we're going to place the 1 hydrogen, the 1 bromine, and the 1 chlorine, and just assume that the rest are going to be fluorine atoms. And so we could have all 3 of these sort of interesting atoms on the same carbon. Let's put them all on the left-hand side. This is 1 isomer. Or we could have 2 of these atoms on one of the carbon atoms and 1 on another. So we might have the bromine and the hydrogen on the left-hand carbon. That puts the chlorine on the other. Or we might have the chlorine and the hydrogen on the left-hand carbon, and that puts the bromine on the other. Or we could have the bromine and the chlorine on the left-hand carbon. This leaves the hydrogen on the other atom. And there are no other combinations that we can get here, so we've got 4 that we've drawn, and so the correct answer is C. Here we're being asked which is a pair of functional group isomers from the selection that we're being shown. So a functional group isomer is a type of structural isomer, and that's where we've got the same molecular formula but a different structural formula. Specifically, the atoms have been rearranged to give us a different functional group. In A, we've got an alkene. They're showing us here hex-3-ene. And they're also showing us cyclohexane. Now, alkenes and cyclic alkanes are functional group isomers, so provided we've got the correct number of carbon and hydrogen atoms, which we do, 6 and 12 respectively, That means that A is the correct answer, and we'd move on if this was our real test. Just to look at the others, just to make sure we fully understand this, B is showing us two different alcohols. It's showing position isomerism because we've got pentan 2-ol and pentan 3-ol. C is in fact not isomers at all. We've got carboxylic acids being shown here, and we've got pentanoic acid and we've got butanoic acid, so they aren't even isomers at all. D is actually showing us position isomers. They're both pent-1-ene in terms of the core carbon skeleton, but on the one on the right, the chlorine's on position 3, so that's 3-chloropent-1-ene, and then the one on the left, we have got 4-chloropent-1-ene, so they are position isomers. So again, A was the correct answer. Okay, that's the end of this video. I hope it was useful. I'll see you again soon.